Dear students, welcome back to my channel. In this class, let us discuss about an important 3-mark derivation, that is expression for energy stored in a capacitor. That is like this, you will get the question. Derive an expression for energy stored in a capacitor. So in my last class I have said about capacitors. Okay, what is a capacitor? Capacitor is a device used to store electrical charges and hence the electrical energy. Okay, so how much electrical energy will be stored in a capacitor? Let us see in this class. See, let us consider a parallel plate capacitor. Which is initially uncharged, that is no charge in it, no charge has been stored. So inside this capacitor, under such condition, let us consider a capacitor. Next, in order to charge it, I will connect it to the source of potential difference, that is typically a battery having a potential difference of V. Okay, fine. It is a plug key. As soon as the K is closed, the capacitor gets charged. Since I have connected this first plate to the positive charge, here positive charge comes, here the negative charge comes. Okay, fine. It's a parallel plate capacitor. See, as soon as the key is closed, charges flow bit by bit. So from one plate to another plate by induction method actually here. Now let us consider one intermediate condition where let us consider an intermediate situation or condition where the charge stored or the charge on the capacitor is Q at similarly, and potential difference between its plates is V, for example. Okay, initially we have considered a capacitor with no charge. Now as soon as we connect this capacitor to a battery which provides a potential difference of V volts, then what happens? It gets charged. Now let us consider a situation where the charge on this capacitor is Q and the potential difference between the two plates of this capacitor, let it be V. That is, we can write Q is equal to C into V, where C is capacitance. What is capacitance? The ability of this capacitor to store the electrical charges. Otherwise, it is the ratio of amount of charge given to it to the rise in its potential. Okay. Now, similarly, V is equal to Q divided by C. For my convenience, I will call this as equation number 1. Next, see. Next, so we have considered one intermediate situation where the charge on this capacitor is Q and the potential difference between its plates is V. Now, let us consider a small amount of work which has been done in order to transfer a small charge from this battery to this capacitor, otherwise from one plate to the other plate by induction method. So you can consider in either ways. Okay. Let dW be the small work done, in transferring a charge dQ to the capacitor at an instant when the dW be the small work done in transferring a small charge dq to the capacitor at an instant when the PD between the plates is V. That is under this situation. Okay. Therefore, dW is given by, we have this formula V into dq, isn't it? While discussing about the concept of electric potential and electric potential difference, I have repeated so many times. Okay, dW is equal to V into dq. What is the value of V? That is from equation 1. We can write it as Q over C into dq from equation number 1. Next, I will take this C outside. Otherwise, this is the small amount of work done in transferring a small charge dq. So therefore, similarly, the total work done in transferring the charge from 0 to Q is, that is from no charge condition to the maximum charge condition. So that is from 0 to Q is given by W is equal to integral 0 to Q dW. So the value of dW says Q upon C dq. So I will take 1 over C outside. It is integral Q dq within the limits 0 and Q. According to the concept of mathematics, that is integration, you know, on integrating Q with respect to this dq, so I mean Q, you get Q square by 2. Therefore, it becomes 1 by C Q square divided by 2. If you substitute the upper limit Q, you get the same thing, Q square by 2. If you substitute the lower limit, that is 0, you get 0. Therefore, it is simply Q square upon 2C. This is the expression for the total work done in transferring a charge from 0 to capital Q. Okay. This amount of work done in charging that capacitor will be stored as electrostatic potential energy. Please remember. Okay. The total amount of work done, so in transferring a charge from 0 to capital Q is W is equal to Q square by 2C. This work done will be stored as electrostatic potential energy in the capacitor. This work done will be stored as electrostatic potential energy or simply electrical energy in the capacitor. Therefore, in place of W, we put U. U is equal to Q square divided by 2C. Please remember, very important question for 3 marks. You may also get it for 5 marks also. See, I will repeat once again. While deriving the expression for energy stored in a capacitor, we have to consider initially we have to consider the situation where there is no charge stored in the capacitor. Okay, I have considered one such capacitor earlier. Next, what I have done, I have connected it to a source of potential difference. So as soon as I connect that capacitor to the source of potential difference, that is battery, so charge will transfer bit by bit. So I have considered one intermediate situation where the charge on this capacitor is Q and the potential difference between its plates is V. Therefore, Q is equal to CV. This equation we know. Next, on interchanging, V is equal to Q divided by C. I have called it as equation number 1. Next, I have to charge this capacitor further bit by bit. So I am considering one more situation. Let dW be the small amount of work done in transferring a small charge dq. So the small amount of work done is given by dW is equal to V into dq. I am doing this work when the potential difference between these two plates is V. Therefore, dW is equal to V into dQ. Next, I have substituted the value of V there. So that is from equation number 1, Q upon C dQ. Next, this is the small amount of work done to transfer a small amount of charge dQ. So, what is the total work done in transferring the whole charge maximum, that is from 0 to maximum Q, is given by W is equal to integral 0 to Q dW. Remaining thing you know till this, W is equal to Q square divided by 2C, and this amount of work done, so by us will be stored as, sorry, not by us, from this battery, work done by the battery will be stored as electrostatic potential energy inside the capacitor, which is given by U is equal to Q square divided by 2C. Please remember. Next, let us go to the other forms of energy. Other forms of energy, that is energy stored in the capacitor. First one, as you know, U is equal to Q square divided by 2C, and the second form, we know that Q is equal to CB, therefore U is equal to C square V square upon 2C. C cancels and it gives you half C V square, isn't it? Since it is an electrostatic potential energy, since it is a stored energy, we are getting half CV square. In case of spring, half K x square. Similarly, half, okay. Next, third one, we know that C is equal to Q by V, isn't it? Therefore, this equation will become U is equal to Q square divided by 2 into Q upon V. Q cancels and it becomes half QV. Q is the charge, V is the potential. So this combination gives us what? Energy. Please remember, if we supply some X amount of energy to the capacitor, it can able to store only X by 2 amount of energy. Please remember, that is only 50% of the supplied energy will be stored in the capacitor. You have connected a battery and we have supplied 100 joule of energy, for example, then it can able to store only 50 joule of energy, like that. Half QV means a capacitor can store only 50% of the energy. Please remember, its efficiency is 50%. Next, I will tell you one small derivation. Actually, this derivation you may or may not get it in the examination, but they will ask at least for 2 marks. Mention the expression for energy density of the electric field, like that. Energy density of the electric field. In this chapter, we consider the electric field between 2 plates of the parallel plate capacitor. In the previous class, we have derived an expression for capacitance of a parallel plate capacitor. In that I have considered one uniform electric field in this gap, isn't it? That electric field is given by E is equal to sigma over epsilon naught. We are talking about that electric field here. Energy density of the electric field means, how can we define the word energy density? Means the energy stored per unit volume of a charged capacitor is said to be energy density. Energy density means the amount of energy stored per unit volume of a charged parallel plate capacitor. That is energy density. It is denoted by small u. Please remember. So I will get you the derivation. the energy stored per unit volume of a charged parallel plate capacitor is called energy density of the electric field. Please remember, we know that the energy stored in a capacitor is U is equal to Q square divided by 2C, isn't it? Let us call it as equation number 1. Now, we know that the electric field in the gap of capacitor plates is given by E is equal to sigma divided by epsilon naught, isn't it? In place of sigma, what we can write? Charge per unit area. Therefore, I will modify this as Q is equal to E A epsilon naught. This is equation number 2. Similarly, capacitance of a parallel plate capacitor is given by C is equal to epsilon naught A over D. Call it as some equation 3. Next, substitute the equation 2 and 3 in equation number 1. Substitute equation 2 and 3 in equation 1. What we get here? See, U is equal to Q square, in place of Q, E square, A square, epsilon naught square, to C, in place of C, epsilon naught A over D. D goes to numerator. Next, what we can cancel here? We can cancel A and A and epsilon naught square and epsilon naught, isn't it? Next, what thing remains here is half epsilon naught E square A into D. I will write A and D inside the bracket because A is the area of each plate of the capacitor, where small d is the distance between two plates, and it gives us the volume occupied by that given electric field. So therefore, I will transfer that A into D. A into D we can write volume. One more step. This is volume. This is U. I will transfer this V to this side. It becomes U by V, which is equal to half epsilon naught E square. U by V, that is energy per unit volume, is energy density, which is denoted by small u. Therefore, half epsilon naught E square. This is the expression for energy density of electric field. You can get it for 2 mark also. Mention the expression for energy density of the electric field and explain the terms like that, they can ask. Please remember, energy density of the electric field means energy stored per unit volume of a charged parallel plate capacitor. Next, how to derive the expression for energy density means by taking the energy stored in the capacitor, U is equal to Q square by 2C, equation number 1. By taking the expression for electric field in the gap of the two plates of parallel plate capacitor, sigma over epsilon naught, in place of sigma. Sigma is charge per unit area, therefore Q upon A into epsilon naught. So I have rearranged the terms. Q is equal to EA epsilon naught. I have called it as equation number 2. Next, capacitance of the parallel plate capacitor is given by C is equal to epsilon naught A by D. That is equation number 3. On substituting equation 2 and 3 in equation number 1, we get up to this. Here, area into distance gives us volume. Next, energy per unit volume gives us half epsilon naught E square. Epsilon naught here is what? Permittivity of free space. Why we have taken the free space here means because we have introduced nothing. in the gap of the parallel plate capacitor. There is nothing. Therefore, we have taken it as free space. Next, E means, as you know, electric field. U is energy density. Okay, please remember. So at least you try to remember this final expression and the definition for energy density. In the next two classes, so we will discuss about the effective capacitance of combination of two or more capacitors in series and in parallel. That in case of resistors in series and parallel. So thanks for watching.